You know, for those of you who are, this makes sense too, hopefully this will make even more sense too, because again, we're building on this idea. So we can use what's called integrated time concentration equations to do some problems with regard to reaction rates. Okay, that's out there on Twitter too, by the way. So that's where I got to. And the way this works is, and we're going to kind of, I've mentioned we're going to use these as a starting place. Basically, what our integrated time concentration equations look like are these for first order and for second order. First order, we call it first order reaction kinetics, second order reaction kinetics. So cool thing is if they come kind of in two flavors. We can calculate the time. So this would be calculate the time question mark needed. Oh goodness. Come back. The time needed to get to a certain concentration, or we can calculate the concentration after a certain time. So those are two broad types of problems that we run into using these equations. So for first order, we talked about with calculus, we can end up coming up with this relationship, which actually matches with this relationship. That's what's called the logarithmic form. And alternatively, and I'm going to go ahead and write it down here on the bottom, this is the exponential form, also for first order, and it can come in very handy. It's just kind of rearranging these or taking e raised to a power, and it looks like this. Molar concentration of A at given time t divided by the molar concentration of A initially is equal to E raised to that. And there's a key on your calculator, I promise you, E raised to the X, E raised to the negative KT. All right. And then for second order, not so surprising, it looks like this. So again, these are the integrated time concentration equations that we used to come up with a straight line to test for 0, first, and second order. And it looks like this. So let's just say we have something that was set its first order. Now, to me, to work a problem like this, you need to be organized like this. If it says first order, you should be saying, oh, well, these are my tools with regard to first order. That's what I would do. So it goes ahead and it says we have an antibiotic and it's going to decompose and it gives us the rate constant. So already, again, what we've been talking about, you're going to see that this is K. That is the real value for K. Isn't that fun? We said that if it's overall first order, which there's only one reactant here, then the units of K should be inverse time, and that's just perfect. So then it goes on to say if a 0.0060 molar solution of an antibiotic is stored at 20 degrees Celsius, and actually this guy right here, this molar concentration, that is going to be our initial molar concentration, A0. The question is, what will be the concentration after 3 months? So guess what? 3 months is going to be the time that we allow. So I don't know if this is working for you, but basically we, let's see, is this right? I think we're going to end up using this form because we have T, 3 months. We have A0, 0.0060 molar, and we're solving for A. That's it. We're going to have a follow-up question with this first order. And in this case, we're after time. How long will it take? So question mark T for the concentration to reach 0.0010 moles per liter. So this would be what? RA. And again, this was our A0, and so question mark T. I don't know if that helps, but that's kind of generally what you're going to see. First order, these are our tools. What's helpful when you work a problem is to actually kind of set the stage. Whenever you see an A working the problem, that's going to be my antibiotic that's decomposing. So to work the first one, I'm going to use this version of first order. Okay. Just because I know to use it. This one, if we plugged in time and the initial concentration, it would be hard to get to the concentration A. This one, we plug in time, initial concentration, it's pretty exposed. We can get to A. Rearranging for A then, A is equal to the initial concentration, A0, which we know, times E raised to the negative KT. Yeah, if you have your calculators, let me find my E raised to the XT here in a minute. So to kind of pull out what we know from the problem, again, the initial concentration of the antibiotic is 0.0060 moles per liter. Notice we need to know the K here, the rate law constant, and it was given in the problem, 1.65 per year was the K, value for K. And we need to know then the time. Now, notice that we're going to take K, which is 1.65 per year, and I want basically my power of E to be unitless. So my K and my T units need to cancel out. So I'm going to have to do some fixing here. Either get my years to months or my months to years. Now looks like I'm going from my months to my years. So I need to convert my time from 3 months to years. So I can take 3 months times 1 year over 12 months. That's exact quantity. And so we're looking at 0.250 years. So that will be the T that I plug in. Then it's very much like plugging in Jenny. Just like you had an equation sheet for your last unit exam, you're going to have an equation sheet for this unit exam. But don't rely on it to basically work the problems for you, because I'm not going to tell you what's what on your equation sheet. Okay? So plugging in looks like this. So at that time of interest, the molar concentration of our antibiotic will be equal to the initial concentration, 0.0060 moles per liter, molar, times E raised to the negative 1.65 per year, 0.250 years. Now again, of course, now our units of years cancel, which is awesome. And if you're like me, this is the sort of problem I have to work a couple times. And if I get the same answer twice, I'm like, yay! This is a TI-84, and I've got a little, it's a shift function, but I've got E to the X. So I probably would take E to the X, and I would probably take negative, and then open parentheses, 1.65 times 0.25, end parentheses, enter, and then I would take that times 0.006. And I would give myself 2 sig figs, give myself 2 sig figs, and this is what I got, 0.0040. And units would be moles per year. It never hurts when you're working problems. Does this make sense? Yeah, it seems reasonable. It started at 0.0060, 0.0040 is what it is after 3 months. I buy that. It shouldn't be bigger, let's put it that way. Let's work the other problem now. And for this one, since we don't know the time, I'm going to go ahead and make the time. I'm going to use this other option for the first order. So rearranging for time, then time is equal to 1 over negative k, the inverse of k, negative k, times the natural log of the ratio of a to a0. So that's the ratio of what a is at time t divided by what a is as it started out. I have some hints at the end for different types of problems you can run into with regard to especially first order. And this actually, sometimes you'll work problems and this will be a percent, you know, or something like that. In this case, we actually know A and A0. So A0, again, was the 0.0060 moles per liter. The K was the same in the second problem, 1.65 per year. And then the concentration of interest, where we're trying to find the time, is 0.0010 moles per liter. So right off the bat, you're thinking, oh, it should be less than a quarter of a year, shouldn't it? Or, yeah, a quarter of a year. So we plug and chug. So T is equal to 1 over negative 1.65 per year. By the way, that term right there, with regard to the units, notice we have units of per year in the denominator. That translates to units of years. The inverse of years in the denominator is units of years. Units of molarity cancel out. So this one's not too bad. By my ln key, which actually is on the same key as my e to the x power. Go figure. Hit my ln key, begin parentheses. Oh, it already began parentheses. Take the ratio 0.001 by 0.006. Enter. And then I would divide that by negative 1.65. 2 sig figs, you get 1.1 years. Oh, 3 sig figs, sorry. Well, it's not 2 sig figs. I'm not sure about that. I'd go either about 1.1 years. The reality is when you go to work problems using the integrated time concentration equations, sometimes they're harder than this. But, not problem. This one's just pretty straightforward. Let's do another one. If you read it a few times, it says we're looking at second order reaction kinetics. Second order kinetics means it's second order with regard to this reaction. Again, it's just a solo one reactant going to basically dimerize. So one C4H6 combines with another one to make C8H12, which is kind of fun. We got K here, so this is K, 144 liters per mole per hour. Again, the units, if it's overall second order, are always going to be liters per mole per time. Initial concentration, that's our A0, 0.0200 moles per liter. So here's our K, here's our A0, and this is what we're going to use. The problem with using this one is it gets kind of messy. They do get kind of messy. So what is the concentration after 1 hour? So this is the only one we got. So we're going to plug 1 hour in here. We have K, we have initial concentration, and we're going to go for A, basically. That's it. How long will it take for the concentration to decrease to 0.0020 moles per liter? So our initial concentration, we were given the concentration of interest, 0.0020 moles per liter. We have K, and we're going to solve for T. That's it. That's totally it. Again, kind of set up what A is equal to, the molar concentration of the C4H6. If we rearrange this, solving for T, oh, sorry. If we rearrange this solving for the molar concentration of A, there's a few ways to do this. Notice that I'm going to actually not go for A. I'm going to go for the inverse of A, just because it's easier. And then what you're going to see at the end is I have to just go ahead and take 1 over basically my answer. So 1 over A, which is I'm after A. Go ahead and plug in what we got. So 1 over A is equal to 144 liters per mole per hour. That's our K. Times the time of interest was 1.00 hours. Our units of time are great. Remember, we had to kind of fix the whole month year last time, but they're fine. Plus 1 over the initial molar concentration of A, which was 0.020 moles per liter. So throughout Chem 1 and still in Chem 2, you have to include your units when you're working problems. I can't remember how I do it on the next slide, but you know, somehow you gotta get this mess. Now, most calculators, mine has an x to the -1 power, so actually I could take these two quantities times each other plus 0.0200 raised to the -1 power. You should come up with the inverse of A, or 1 over A is equal to 194. 3 things, and your units actually are going to be liters per mole. Liters per mole, like what the heck? The liters per mole is the inverse of moles per liter. So if you kept your units, you're like, oh, I know I still need to flip it. So one last thing then, I can't remember how I do it, is if you take 1 over 194 liters per mole, you are going to get 0.00515. And then the units would now be moles per liter. Straightforward. First order, this. Second order, this. And you will have on your unit exam these equations. They might be all totally scrambled, but you'll have them there. You'll have to recognize that.
I was wondering if you'd be willing to meet with us. Like the calculator just keeps saying syntax error. I don't know what I'm doing. So I don't know if it's like in the wrong.
Yeah, it does look like it's
system.
Yeah,
but yeah, we can do that after
yeah,
class.
we can, because yours looks like it's kind of funky. Got a mind of its own right now. So we have a follow-up question. In this case, we were going after the molar concentration. In this other case, we're going after T. So we can rearrange this, and it looks like this, where T now is equal to 1 over K times quantity, the inverse of A, or 1 over A, minus the inverse of A0, or 1 over A0. Okay, and this is what we have to deal with here. This, like, if you're like me, I wish they would have had a different. These look like the same number to me if I'm not careful. Like, they're not the same number. Okay. So time is equal to the inverse of K, 1 over 144 liters per mole per hour, times this quantity, which this one's the inverse of the molar concentration in question, inverse of 0.0020 moles per liter, minus the inverse of the initial molar concentration, 0.0200 moles per liter. Yeah, this one just, I have to do this one a couple times, make sure I'm getting my calculator right. But what you end up with is a value of 3.1, and notice that your units are going to be hours, because actually the units here, quantity-wise, the units here, aside from the quantity, are going to be moles per liter in the denominator, which is liters per mole. And here, this is liters per mole, so it's the denominator, so it's moles per liter, and they cancel out, which actually just leaves you the units per hour, so it came along with the K. So anyway, that's it. Have an answer on that? That's your answer. A few more tips I'm actually going to add to this. And we're only going to get through this part. I'm not going to go on the next part today. We're doing good for time. So, there are some cool tools that we can use, and they deal with what's called half-life. Half-life, by definition, is whatever molar concentration you start with, it's the time that it takes to get half of it gone. That's half-life. That's it. That's half-life. Half-life variable is the T 1/2. Get it? Time 1/2, half-life. That's half-life. And so we could actually say then the half-life is the time when your concentration of interest, okay, is equal to half of your original concentration. So mathematically, that's what it means. We're going to do some substituting here so that you actually get a half-life equation for, I think, first and then second. So it's time when A is equal to 1/2 of A0. Makes sense. So if we turn our attention to first order, okay, we know that with regard to first order, this is the relationship between the original molar concentration, A0, the molar concentration at time t. Well, if we do some substituting in, where for A, we're going to substitute 1/2 of A0, because that's what we said by definition half-life is. If we do that, then actually T over here is not just any T. This T is T 1/2. Make those substitutions. Of course, you can probably see what's going to happen here is that our A0 terms are going to cancel, aren't they? These two A0 terms. So for first order only, this thing kind of boils down to something like this, where it's the natural log of 1/2 is equal to negative K T 1/2. I got one more form of that. So I'm running out of room for my first order. So half-life for first order is equal to 1 over negative K ln of 1/2. Now actually the ln of 1/2, we can put it in our calculator. Natural log of 0.5 Oh, sorry, I guess we're not doing that. I'm using one of the log laws. So that sheet I gave you the other day, actually I think this is a couple of them, where we're basically absorbing this negative into my log and kind of flipping it, making this a 2 and this a 1. And so this is what you're going to see on the test, I think. So that negative goes away, and this is the ln of 2, and I'm going to put it over my K. But you could actually, that's really actually a number too. So if we take a step back and look at it, notice that the half-life is independent of the initial concentration. A0 doesn't appear there for first order. That's kind of fun. I have some pictures to kind of show you what half-life might look like. So this is the decomposition of hydrogen peroxide. And this is 1 molar, and how dark green it is, which I don't think hydrogen peroxide is dark green, that's okay. How dark green it is means how concentrated the H2O2 is in your water. So 1 half-life would be this. Does that make sense? I can't see much of a difference there. If I went from 1 molar to 0.5 molar, okay, so that is a half concentration. So that means that 6 hours, or 2.16 times 10 to the 4th seconds, is its official half-life. So to go from 0.5 to what? 0.25, then it should take 6 hours. Okay, so this should take another 6 hours, and it did. This is 12 hours down the road. Okay, so another 6 hours down the road puts us at what? 18 hours total, and it should be what? 0.125? And I have one more, another 6 hours down the road, 24 hours, and you're half of 0.125 molar, which is 0.0625. Okay, so that's kind of how half-life works. Another way to look at it would be this, which this is a different reaction. But along the y-axis, you have concentration in the form of the partial pressure of this gas. And then along the x-axis, of course, you have time. So if it starts at 800 millimeters of mercury, 400 millimeters of mercury, it would be half converted. So you're looking at, what, 80 minutes? So if it goes another 80 minutes, total of 160 minutes, you would expect that it should be half of the 400 should be used. So talking down to 200. And give it another 80 minutes, and you're out to 240. So half of the 200 should be used up, so it's at 100. So that's kind of what we need, a half of first order. Okay, well, let's do a similar thought process with regard to second order. This is the time concentration, integrated time concentration equation for second order. And if we substitute in for that, the A, we're going to go 1/2 A0. And then for our T, that's going to be the half-life. And it's going to fall out a little differently. So in this case, we've got the inverse of 1/2 A0. Are you serious? So that 1/2 actually comes up and flips. That's the same thing as 2 over A0. So you have 2 over A0 minus 1 over A0, which is equal to what? 1 over A0, right? Okay. So that's 1 over A0 is equal to KT 1/2. And then solving for the half-life, then half-life is equal to 1 over A0, also in the denominator is K. So I'll put that right there. Second order reaction kinetics. The half-life is equal to 1 over K, also in the denominator is your original concentration. So notice that this is different then, that the half-life does depend on initial concentration. Also, it depends on K. Where the half-life over here depends only on K. All right, some tips in working your problem. Keep in mind that the specific equation to use depends on whether it's first or second order. I tried to make a big hairy deal of putting this on the board because my mind has partitions in it sometimes, and this is one of the places that has to have partitions in it. Also, some tricks is if the reaction order isn't stated, but your K is given, do a little bit of detective work and do what we talked about before. Use the units of K to backtrack to what the overall reaction order is. And if there's only one reactant, then guess what? Then that's the reaction order that reacted. If K isn't given, there should be enough information to find it. For example, if K isn't given, but your half-life is given, and it's first order, you can go ahead and find K. We have a half-life. We can rearrange this to find K. Oh yeah, so the other thing is if K isn't given, but if you are given the concentration after a given amount of time, you can find K. Do you know what you can actually find K for both of these in that case. So for instance, if you're given the initial concentration, the concentration at time t and time t, well, you can find K. Okay? So that. And I mentioned this a little bit ago, that if you are, especially with first order, if it says how long will it take in order to have half of A left, 0.5, half of A left, then actually you're looking at the natural log of 0.5 here. You don't need to know the initial concentration and the concentration at time t, okay? Or if it says how much time will it take to have only like 80% of A left. So 80% of A left would be, what, 0.8 here. So, right. And I'll turn on these, which will we do on Wednesday. Did you take a look at your calculator?
I think yes, we do set up for something.
Anybody have a calculator like?
It's a Casio X115. I could take it down to the
I'll take a look. Glenn.
I have one kind of like it. It's a